Look at these two environments running the exact same model. On the left, the predictions are failing. On the right, they are nearly perfect. Both systems are running identical code on identical hardware with zero difference in training time. This performance jump from machine learning, we aren't reprogramming the algorithm. We are meticulously curating the evidence it uses to learn. AI has no innate understanding of our world. Its perceived intelligence is a direct reflection of these carefully structured human inputs. To understand this, we first need to define a feature. At its simplest, a feature is any measurable piece of information about an object. In a house price dataset, your features are basic numbers: 2,000 square feet, 4 bedrooms, and 3 bathrooms. To the algorithm, House A and House B look identical because they share these exact same data nodes. In reality, House A is next to a desirable transit hub, while House B is adjacent to a noisy factory. Because the machine can only read the numbers we provide, it will fail to predict the price difference unless we translate that physical reality into a mathematical format. Humans must step in to bridge the gap between messy reality and the rigid logic of the machine. Raw data often looks like these disjointed fragments. They contain information, but offer no clear path to a conclusion. Feature engineering is the act of connecting those fragments to reveal a broader, actionable pattern. We can turn a static birth year into a dynamic age feature, providing the model with immediate relevance. Similarly, converting a purchase date into days since purchase allows the model to track time-based behavioral trends. Dividing a salary by a loan amount creates a debt-to-income ratio, a far more predictive metric for credit risk than those two numbers alone. Even raw latitude and longitude coordinates are often combined and transformed into a single feature: distance to city center. These newly created features inject human intuition directly into the algorithm's logic, simplifying the mathematical relationships the machine needs to learn. This manual process is the invisible engine behind everything from medical diagnostics to fraud detection. There is a common belief that modern deep learning systems automatically learn these features on their own, without human intervention. However, feature engineering remains essential for traditional spreadsheets, small datasets, and any model where we need to understand exactly why a prediction was made. No matter how sophisticated a neural network becomes, the foundation of its knowledge still depends on human curation. The 95% accuracy we saw earlier was the result of a superior teacher providing better features, rather than a more powerful processor. In data science, the quality of the input determines the quality of the prediction. But what happens when you give an algorithm too much information and it becomes overwhelmed? To solve that, we use feature selection, the next step on our path to thinking like a data scientist.